Hey, all right, last video for Unit 5. This is going to be a quick look at, little deeper look at Catalyst. All right, share my screen. Share. Oh man, I hate it when that happens. There we go. Come on. It's taking a little, there we go. Longer than normal. Okay. Catalysis. Fancy word for catalysis. Okay. I don't want pink. Let's write dark blue. So catalysis. We know that a catalyst speeds up a reaction. All right. And it does that by offering an alternative pathway. That alternative pathway has a lower activation energy. It facilitates everything that has to do with collision theory, which is more collisions and proper orientations. Okay, so when a catalyst works with the collision theory, right, it helps to provide everything that's needed. There are two main types of catalysts. There are homogeneous catalysts, all right? And in that sense, the catalyst is in the same state as the reaction. Okay, that could be like C2H5OH aqueous plus H plus. This is an acid catalyzed reaction. All right, would yield C2H5OH2 plus. That would be an intermediate, okay? And what we see is everything is in the same state. So it's a homogeneous catalyst. Notice here that we have actually, this is your catalyst here, right? And we have actually, the catalyst has actually formed a covalent bond, right? With one of the substances, right, with the reactant. And that gives us a different structure, right, different bonding structure. And that gives us a different potential energy. All right, so what we see is, in effect, we're going to have an alternate pathway. It's all those things. It's going to require less energy, and the reaction is going to happen more quickly. Simple, a homogeneous catalyst is in the same phase as the reaction. Therefore, we could look at a heterogeneous catalyst, and that is where the catalyst would be in a different state than the reaction, okay? And let's look at an example like this. Let's draw like a metal here. You can make it as big or small as you want, or you can just draw squares. But this is going to be like my platinum, PT. This will be a solid catalyst. And what happens, all right, is let's just have some gaseous molecules here. And let's have maybe something like this here. Okay. And what these gases will do is they will absorb onto the solid catalyst, all right? And then they will react And in that reacting, maybe, you know, I'm just kind of coming up with something. Maybe we get something like this, you know, something different. And those are attached. And then what they will do is they will deabsorb. Desorption, maybe I can call it desorption. I think I can. Desorption. So, you know, desorption. I'm not sure if that's a word. This is adsorption. All right. So basically, these gaseous molecules absorb into the platinum solid catalyst. They this allows them to become more fixed in place, right? Makes sense. So they were gases all spread apart. Now they're more fixed in place, and this increases the likelihood, right? Increases collisions and aids once again, and aids in orientation. Okay, so we have, or we're facilitating the processes that are required to have effective collisions, which is required for a reaction to occur. So the gaseous molecules come in, they do their thing, they exit. That would be a heterogeneous catalyst because we've got the catalysis in a different phase in the reaction. A real life example of that is a catalytic converter, which is in your car. Okay. And what it does is it's made up of different metals, maybe platinum, palladium, metal oxides, copper oxides, chromium oxides, and they adsorb. I'm horrible with that. They absorb the carbon, right? We have a combustion, right? In the catalytic converter, we have what we call incomplete combustion. All right, oops. And that produces CO, carbon monoxide, right? Dangerous. You do not want it building up in your car, and we don't want to put it into the environment. So the catalytic converter will absorb the carbon monoxide, changing CO into something safer, into a safer gas, maybe carbon dioxide, right? It'll also absorb nitrous oxides and take them to a process of changing them into safer gases, right? Safer for our environment, safer for us. One more thing I'd like to look at would be this example here, okay, right here. And you are offered two mechanisms. Mechanism 1, which has 2 steps, and mechanism 2, which has 3 steps. All right, and a student claims that the first mechanism is faster due to having fewer steps. I need you to agree or disagree and justify. All right, so we would need to start by agreeing or disagreeing. That always needs to be your first part of your answer. If you need to figure out how to get to your agreeing or disagreeing, maybe leave a couple spaces and then start doing your thinking process here. But the first part of your answer needs to be agree or disagree. Now, you should pause and think about making an answer, making a claim for your answer based on the evidence, okay? So here's my answer. Yes, both mechanisms, or yes, mechanism 1 only has 2 steps, and mechanism 2 has 3 steps, which is obviously more. And both mechanisms give us the same overall balanced equation. However, mechanism 2 has a catalyst whereas mechanism 1 does not. Catalyst speed up reaction rates by lowering activation energies. So I would propose that mechanism 2 would be faster. I don't think that the number of steps has an effect on the rate, but the presence of the catalyst does. All right. I disagree. Both mechanisms lead to the same overall reaction, but mechanism 2 has a catalyst. The catalyst will speed up the reaction. The number of steps is not a factor. Okay. That's it, guys. I'll see you later.